So the integrated rate law is the basis for why we could use a graphical analysis to determine the order of the chemical reaction. In the previous video, I showed you how to plot your concentration data as a function of time in order to determine whether the reaction was first or second order. And so in this video, we're going to take a look at where that technique came from. And it came from the integrated rate law. So if we look at the first order rate law and then integrate it, it'll look something like this. So you can write the rate law here. Rate is equal to the negative change in concentration of reactant A over time, which is equal to the rate constant times the concentration of A, right? This is a simple first order reaction where you just have reactant A becoming products. So the rate law looks like this. When you integrate that, which if you haven't had calculus yet, you may not understand what integration is, but you can still use the result of the integration, which looks like this. The integral of this equation with time is equal to the natural log of the concentration of A at some time t, and that t is just any point in the future as the reaction progresses, over the concentration of the reactant A initially. So the sub-zero here represents at time zero, or the initial concentration, which is equal to negative kT. So this equation here is a result of integrating this expression. Okay, so we can do some simple substitutions here and rearrange it, and we'll see where the relationship for the linear dependence of the natural log comes from. If you remember from your log rules, the log of the ratio of two values is equal to the difference of the logs of those two values. So ln A sub t over A sub 0 is equal to ln A sub t minus ln A sub 0. We can rearrange this and substitute for the fact that this is also equal to negative kT in order to get this expression here, which is that the natural log of the concentration at some time t is equal to negative kT plus the natural log of the initial concentration. And you'll notice that this is the equation of a line, right? Y is equal to mx plus b. And so we have a plot of the natural log of A with time, y with x, would be linear. And in fact, we can also obtain the value of k, the rate constant, from this expression because it's the slope of the line. And in fact, the y-intercept value is the initial concentration. Okay, so we can see that you can take this information and apply it to the example that we used for the graphical analysis technique, or that I used for that video, and we will do that in a moment. But first we're going to examine integration of the second order rate law. The second order rate law would look something like this, right, where you have a reaction that depends only on the concentration of A, but is second order in A. So if you integrate this expression, the result is this expression. So 1 over A at some time t is equal to the rate constant times that t value plus 1 over the initial concentration. And in this case, a plot of 1 over the concentration of A with time is a straight line. And so there you have your relationship for the linear dependence being a second order when you're plotting the inverse of the concentration as a function of time. Okay, so let's go back and take a look at the example problem that we did in the previous video. You have a linear dependence of 1 over the concentration as a function of time. And then we saw that the slope of this line is equal to the rate constant. So if you're in Excel, you can simply show the equation for this line on the chart. And from the equation of the line, you can obtain the value of the slope, right? So we have the slope of 0.7511, which again corresponds to the rate constant k. Now 4.0067, that's the y-intercept, and that is equal to 1 over the concentration. So if you take the inverse of 4.0067, you actually get a value that's really close to 0.25, which you can see over in cell B2 is the initial concentration. So again, y-intercept is 1 over concentration, slope is k. If for some reason you haven't yet watched the video that I just posted on graphical analysis technique, let me recap for you what all this information is. So we had learned that if you plot the natural log of concentration as a function of time and you obtain a linear relationship, then you can conclude that the reaction is first order in that reactant. In this case, the reactant was NO2. We were looking at the reaction between carbon monoxide and nitrogen dioxide. And these were data presented in a practice exercise in your textbook, Gilbert 5th edition. So we took the initial data given there, plotted that, and observed that the data was not linear. Then when we plotted the natural log, it looked more linear, but the most linear data was when we plotted 1 over the concentration of the NO2, which gave us an R-squared value of 0.9998. So that was essentially the correct answer, meaning the order for NO2 in this reaction is 2. In this case, the rate law for the reaction would be rate is equal to the rate constant K times the concentration of NO2 squared. And then that rate constant K is just the slope of this line, which is 0.7511. Go ahead and send me an email if you have any questions on that. And I guess the lingo is stay tuned for another video on the next subject in this chapter.